Okay, this is our last lesson for the week. All of your work is due on Sunday because I'm so late putting up the videos for everything. Everything else has been up all day, but you know, we didn't have school Monday. Tuesday, yesterday I was working on putting everything up. I finished it this morning, so it's been up today, but the videos have not with it. So since I'm so late in putting everything up, I'm giving you guys through Sunday. You are welcome to have it turned in by Friday. Don't think I'm expecting you to use your weekend to do it, but I am giving you that extra time if you need it. That should be plenty, more than enough time. All right, so for this last lesson, I was just going to fill out a study guide again like I've been doing, but I think this last lesson actually does need the notes. We need to go through everything, so I'll try and do it quickly, but I am filling out the blank notes for you guys. All right, so our essential question is, why is it important to think logically? It's kind of the central theme in all of these proofs is just a logical progression. What are the steps to solving something? Why is it important to think logically? All right, so we have two new rules that we're learning up here. One of them, we're not really going to use it that much, like at all. But the second one we're going to use all the time. That's what the rest of the notes are based off of. So the ruler postulate just says that the points on a line can be matched 1 to 1 with real numbers. Points on a line can be matched 1 to 1 with real numbers, meaning I can draw a number line and I can spread out the numbers really far, or I can put them really close together. But however I draw it, it matches 1 to 1. Like 1, 2, 3, 4, 5, 6. It's fine. Okay, we're not going to focus on that. The second one is important. This is the segment addition postulate. So if B, point B, is between points A and C, doesn't matter where, doesn't have to be in the middle. It can be way off to one side, but as long as B is somewhere in between A and C, then we can say that segment AB plus BC equals the whole thing AC. So if point B, which is this guy right here, is somewhere in between points A and C are our endpoints, then we can say that this segment, one endpoint to point B, plus point B to the other endpoint, this segment, adds up to, these two segments together add up to the entire thing endpoint to endpoint. That's all we're saying. So it doesn't matter where we put B. I could draw a line and put A here and C here and draw B way over here. But it's still true that this whole piece plus this little piece adds up to the entire thing. Oh, you can't see that where I'm drawing, sorry. I can put B way over here. I could put B in the exact middle. I could put B way over here, but it doesn't change the fact that from one endpoint to B plus B to the other endpoint adds up to the entire line endpoint to endpoint. All right, so we're going to use that a lot in our proofs today. Justify the steps for the proof of the conditional. If AC equals BD, then AB equals CD, right? So here's our given. AC equals BD, and it gives us a picture. So we're going to use this picture. It doesn't always tell us everything in the given. If there's a picture, this also gives us information just as much as the written given. Okay, so here we can mark these congruent. So this whole thing AC from here to here is the same size as B to D. This whole guy is the same size as this whole guy. Okay, so when we say that, step one, why did we say that in step one? Because that's what was given to us. Step two is our segment addition postulate. AB plus BC equals the whole thing AC. This first piece plus this second piece here, B to C, equals the whole segment A to C. Okay, and then in the same respect, line BD is made up of this first part plus this second part. BC plus CD equals this whole thing, right? So that's our segment addition postulate. We always put the rules for why we use this step over here. We put these to the side. I'm going to put segment addition post. You could put seg add post. That's fine. Okay, step 3. Now we're going to start combining some of these steps. AB plus BC equals BC plus CD. Okay, well, how do I know they're equal to each other? Well, I started off up here, and then I said AC is the same thing as AB plus BC, right? And I said that BD is the same as BC plus CD. So I replaced BD with BC plus CD. So this is AC. This whole thing is BD. So all I did was substitute. I put something in its place that was worth the same amount. This is substitution. If this whole big segment is made up of these two smaller segments, then these two smaller segments added together is the exact same size as the big segment. So if I said AC, I could just replace that with AB plus BC. They're the same size. Same thing with BD. It's the same size as this. So since I know AC and BD are equal, I know this guy is equal to this guy. Okay, and then to get from step 3 to step 4, what happened? Well, I see the ABs match up. I see the CDs match up. So what did I lose? I lost this BC and this BC. Well, if both sides of my equal sign have a BC, and here neither side does, but they still have the other pieces, couldn't I just have subtracted BC? Couldn't I have just said AB plus BC equals BC plus CD, and then just said minus BC over here, minus BC over here. These go away, and I'm left with AB equals CD, which is what I have here, right? So that was just the subtraction property of equality. All I did was subtract from both sides of my equal sign the segment BC. Remember, whenever we write a segment without a line over the top, we're not actually talking about the segment itself. We're talking about the size of the segment. I don't know what the size is, so I can't say 5 or whatever. I have to call it something. But whenever I write a line like this with nothing over the top, I'm talking about the size of the line. Let's do another one because that was kind of confusing, right? Let's do another one and see if they start making sense. Okay, same thing, segment addition postulate. Prove that if AC is equal to DF, so this entire thing here is equal to this entire thing here, and AB equals DE, so this little segment is congruent to this little segment, just this front part, it's congruent to this part, then we have to prove that this second part must be equal to this second part, right? If from A to C that was 10 units, and DF is the same size, then D to F is 10 units. If this first part was 3 units, and this is 3 units, and the whole thing is 10, then I could easily say that this has to be 7, and if this is the same size, 10 and 3, then this would have to be 7. So how do I put that into proof form? I know it kind of makes sense, but how do I put it into proof form? Well, I start off with line 1, the given. AC equals DF and AB equals DE. So the size of AC is equal to the size of DF, and the size of just the first part here, the first segment, is equal to the size of the first part here. And that's given to me. Okay, I'm trying to get to BC equals EF. That's my goal, is to get this on the bottom. So how do I get there using the segment addition postulate? Well, I know that AC is made up of AB plus BC. And I also know that this entire line segment on the bottom, DF, is made up of DE plus EF. And I already said up here that AC is equal to DF, the entire thing. So couldn't I say that this whole guy is congruent to this whole guy? If this is congruent to this, then I know this has to be congruent to this. So I'm going to say AB plus BC has to be the same size as DE plus EF. Okay, well, that's all fine and good, but then what do I do? I'm going to go back and write in the steps here in a second. I want to go through my logical progression first. Well, I got to this point. I just want B, C, and EF. Right now I have B, C, and EF, but I also have an A, B, and an D, E. Well, what does it tell me up here in the given? It tells me that A, B, and D, E are equal, right? So couldn't I replace, anywhere I see a D, E, couldn't I replace it with an A, B, or vice versa? Yeah, I absolutely could. So down here, I'm going to do that. AB plus BC equals, and instead of writing DE again, I'm going to replace it with AB. Because again, DE and AB are the same size. It tells us right there. So I just used substitution there. All I did was substitute AB in place of DE. They're the same size. But now in step 4, I have AB on both sides of my equal sign. So to get from step 4 to step 5, all I have to do is subtract AB from both sides. Right? And once I get rid of AB on both sides of my equal sign, I'm left with BC equals EF, and that was my goal. So wait, what? We just had to think through it logically. So number 2 up here, I said the entire line segment is made up of these 2 smaller segments. That's the segment addition postulate. This whole thing is made up of these 2. So I can say segment, add, post. Segment addition postulate. Same thing with DF. The entire line DF is made up of DE and EF. Okay, then from that line to the next line, what happened? Well, I know that AC is equal to DF, and I know that AC is the same thing as AB plus BC, and DF is the same thing as DE plus EF, so I just use substitution for line 3. Okay, once I use substitution here, then going from line 3 to line 4, the only thing I did was rewrite DE as AB. I replaced DE with AB because it told me up here in step 1 in the given that they're equal. And if anything's equal, then I can interchange it, right? I can replace it. So that again is substitution. And then getting from line 4 to line 5, I had to subtract AB from both sides of my equal sign. And whenever I subtract the same thing from both sides of my equal sign, that is the subtraction property of equality. So there's my proof. I know it's confusing. I know, guys, I know. Some people love proofs. Most people can't stand them. This is the easy stuff so far, so just try and stay with me. It's logical progression. If you don't get it, you're not alone. You are okay. We're going to keep doing these examples over and over until maybe, hopefully, fingers crossed, it starts clicking. All right, properties of segment congruence. There's a long-winded, wordy part here that I have to write. All right, segment measures are reflexive. So like we could say segment AB is equal to segment AB. That's reflexive. They're also symmetric. So I could say AB equals CD or so CD equals AB. I can flip-flop them. And they're also transitive. Transitive would be if AB is equal to CD and CD equals EF, then AB equals EF. Then I cut out the middleman and say AB equals EF. Okay, so segment measures are reflexive, symmetric, and transitive. And since segments with the same measure are congruent, since segments with the same measure are congruent, the congruence of segments is also reflexive, symmetric, and transitive. This is the stuff in math that I don't like because it just feels like we're saying all these words and I have no idea what I just said. You know, like when you read a book and it's written in like Old English or something, and you're like, what the heck? Why can't they just talk normal? And they are talking normal, but to us, it doesn't make sense. It's kind of like with math. All these words, blah, blah, blah. Just cut it down to what the important part is. All this is saying is, if stuff is equal, it's also congruent. If stuff is congruent, it's also equal. That's all it's saying. So we already have our reflexive property of equality with an equal sign. It's the exact same thing as the reflexive property of congruence. We're just using a congruency sign. So we would say here, AB is congruent to AB. So now we're not talking about the size. Before we were talking about the actual measure of segments, the size. And we didn't put the little line over top because we were talking about a mathematical measurement, right? AB, the length of AB is equal to 6 units. So AB is equal to AB, meaning 6 equals 6, right? That's not what we're talking about here. Now we're just being more general. We're saying a segment out there exists, and that segment is congruent to itself. I know that sounds funny. We're going to use it later. I promise it'll end up making sense. But for right now, that's all this is saying. It's the same exact thing we've already gone over. The symmetric property of congruence, same thing as the symmetric property of equality. If AB equals CD, if AB is congruent to CD, then we just flip-flop them and say CD is congruent to AB. Telling you guys, exact same thing. We just use the congruency symbols instead of the equal signs. Everything else is exactly the same. Okay, if AB is congruent to CD and CD is congruent to EF, then I can just cut out the middleman and say that AB is congruent to EF. Just like the transitive property of equality. That's all we're saying. Congruency is equality. Same basic idea. Okay, so let's fill out another proof. I'm almost done. Hopefully, if you're sticking with me, I appreciate it. You guys are being patient. Hopefully, you have stuck with me. Okay, so given that segment JL is congruent to segment KM, now all of our rules are going to be on congruence and not equality. And we can switch back and forth, so I'll show you that here too. Given that JL is congruent to KM, I have to prove that JK is congruent to LM based off of this picture. So if I know that this whole thing here is congruent to this whole thing here, then I have to prove that this little guy is congruent to this little guy. That's what we're talking about. All right, so it kind of gives us the stuff here, the bones, and we have to fill in the blanks. JL is congruent to KM, that's given, okay? Then immediately, what did I do here? This says congruent, this says equals. These have lines over top, these do not. So what's the only thing I did here? I just went from congruency to equality, right? This is the definition of congruence. Definition of congruence just says that if two things are congruent, it means their measures are equal. If two measures are equal, it means their segments are congruent. It means they're the same thing. We're just flip-flopping in between how to write them. If it's congruent, it's equal. If it's equal, it's congruent. Definition of congruence. Okay, so the next step, I say, I know it's going to be segment addition postulate. JK plus KL, this guy plus this guy, has to equal the whole thing, which is JL. And then KL plus LM has to equal this whole part, which is KM. And it tells us that's a segment addition postulate. So then I can say that JK plus KL, this guy plus this guy, is equal to KL plus LM, KL plus LM. Because it already told me JL and KM are congruent, and I just said what they're equal to. So this is substitution. See if I can figure out a visual way to make that make more sense, okay? I said JL is equal to KM. Then I said this whole thing is JL. JL is equal to JK plus KL. So I replaced it there. This statement is the same thing as this statement. They're the same thing. Do I have another highlighter? Hang on, let me see. Please have a highlighter. Please have a highlighter. Aha. Oh, maybe. I've got orange. We'll try orange. Okay. Hopefully it works and it's not dried out. So we'll highlight Km in orange. Then it tells us this is what Km is equal to. Right? So all I did was replace. I took this guy, JL is equal to Km. JL is the same thing as this whole. And Km is the same thing as this, all this. So instead of saying JL, I replaced it. And instead of saying Km, I replaced that. So this is the same thing as this. Just substitution. Made it look a little different. Okay, then I notice that I subtracted KL from both sides of my equal sign. So whenever I subtract from both sides of my equal sign, that's the subtraction property of equality. So in the next step down, I have to actually subtract it. So those go away, and I'm left with JK equals, these KLs go away, LM. And all I did was simplify here, so that's substitution. You don't have to write simplify, I'm just writing it for you. Just write substitution. So all I did was subtract here, I'm here, and since this is no line on top, equal sign, and I have to prove that the two segments are congruent, just like I did from step A to B when I changed it from congruent to equals. That was the definition of congruence. Now I'm changing it back. I lived in this other world for the middle part here. I was all in the equal sign. Now I got to flip-flop back to congruence like I started. So again, that's definition of congruence. Same thing. So JK is equal to LM. JK is congruent to LM. Same thing, they're just written differently. Hopefully that makes sense. Okay, let's do another one here together. All right, this is kind of long, so we'll go through it fast. E is the midpoint of DF. Here's DF. E is in the exact middle. If E is the midpoint, that means this segment DE has to be equal to this segment EF. That's the definition of midpoint. If E is in the middle, it separates our segment into two smaller half segments. We have to prove that DE is equal to 23. So we have to prove that this is equal to 23. What the what? All right, step one, this is our given. So we write given. Done. Step two, I know the reason is definition of midpoint. So what is the definition of midpoint? It tells me that when I have a middle point on a line, that the two segments created are equal. So I can say that DE is equal to EF. That's my definition of midpoint. Okay, fantastic. So what is DE equal to? DE is equal to 6x plus 5, and EF is equal to 8x minus 1. So I'm going to substitute. In place of DE, I'm going to substitute 6x plus 5. And in place of EF, I'm going to substitute what it's equal to, 8x minus 1. So that's substitution. Awesome. So now I can actually solve, right? So to get from this line to line 4, what did I do on both sides of my equal sign? Well, I have a 5 here, so it looks like I got rid of 6x. 8x becomes 2x. Yeah, I definitely subtracted 6x from both sides of my equal sign. So that's the subtraction property. One thing that you might notice, and it's really a pain in the butt because they don't keep it the same. Like, I'm a creature of habit. I want, like, if you're going to do something, do it the same way every single time, and then I'll catch on. If you're going to change it on me all the time, I'm going to get confused, right? And that's kind of what they do when they set up these proofs. Sometimes they make this 2 steps. And in one step, like, it's like we skipped this step where we said 6x plus 5 minus 6x equals, let's scoot over, 8x minus 1 minus 6x. Remember how in the other proofs they actually wrote this step out where they showed that we were subtracting 6x from both sides? And we would write subtraction property. And then the line beneath that is where you actually simplified it and you'd write substitution. Well, here we're skipping that step. Here, we're not going to do the baby step of writing out what we're doing. Here, we kind of do this step in our head. So we go straight from here to simplifying, right? But instead of, since we still subtracted, we can't say subtraction and then substitution. From here to here, we're just going to cut straight to subtraction. We just kind of cut out a step, the substitution step. Okay, and then from here to here, this is the addition property of equality. So what am I going to add to both sides if I'm trying to get x alone? I'm going to add 1 to both sides, right? So if I add 1 on both sides of my equal sign, I get 6 equals 2x. Okay, and I'm still trying to solve for 6. Going down to the next line, it says I use division property of equality. So what do I need to divide here? I need to divide both sides by 2. So 6 divided by 2 is 3. 2x divided by 2 is x. And again, we skipped that step in between where we showed it. We didn't show that little middle step where we divide both sides. But just know that it happened. We just went straight to simplifying. We kind of did it the big boy way this time. We cut out that baby step. All right, so now we have 3 equals x, division property of equality. Fantastic. So then what? We're going to use another part of our given, right? It doesn't tell us this up here, but it does show it to us in this picture right here. So it says DE equals 6x plus 5. That's given. So if I use DE, because I have to prove that DE equals 23, I'm going to substitute what x is. In line 6, I just found out x is equal to 3. So I know the segment that I'm looking at is DE. I know DE is 6x plus 5, and now I know x is 3. So I'm going to substitute 3 in place of x. And then 6 times 3 is 18. 18 plus 5 is 23. All I did there was simplify, so that's substitution again. Seriously, please don't get frustrated. I understand that this is like, wait, what? What? I get it. I promise you, I've taught this for many years. I understand where you're at. Just trust me when I say that we're going to keep doing so many of these proofs that after a while, you'll get kind of the hang of it. You might not love it. You might not get to be an expert at it, and that's okay. But you will, I promise. If you stick with it, you will kind of fall into a groove and understand, okay, all right, I see where they're coming from. I get it. All right, I'm going to skip this bottom part, find the error, because we've done enough notes, and we're going to stop on that point. So all we're doing in this whole entire lesson is using segments, right? The segment relationships. If I put a dot in between 2 endpoints, it creates 2 segments. Those 2 segments add up to 1 big segment, right? That was the main thing, the segment addition postulate that I used in this whole lesson, and we just used it in proofs. So I'll leave you the assignment, and tomorrow and Friday, if you attend the Q&A, I'll be happy to answer any questions that you have on this stuff. Okay? Thanks, guys.